Okay, in this video we're going to look at the first two sections of Chapter 7, which is all we'll be covering in Chapter 7, on modular arithmetic. So, modular arithmetic is something that we do all the time, probably without realizing it. Like, if it's 10 a.m., and we want to know what time it is 5 hours later, we know that that would be 3 p.m. Of course, you could call that 1500 hours if you want, but we're going to stick with the normal way of telling time. So we don't say 15 o'clock, that's for sure. So we already sort of cycle around the 12 and go 1, 2, 3. So, and we do this also with seconds and minutes as well. We count up to 60 and then we return back to 0. So if you had 45 minutes and you wanted to add a half hour, it would be something 15. So what is this in general? Well, before we can dive into it, we need to first talk about the division algorithm, which says that, if you want to divide a number a, an integer a, by another integer b, then we're saying that b goes into a some number of times, so say q times, and has some remainder of r. It's possible that you have no remainder, then we'd say it goes in evenly. And this remainder could be 0, but it has to be strictly less than b. If it was bigger than b, then we would say it goes in more times than that. And that's really the important part here, because while this makes sense while this is probably pretty clear for everyone for positive integers, for negative integers, maybe we have to think a little bit more. So these two operations that we see here, mod and div, we'll mostly be focusing on mod, but the mod is the remainder, while the div is this quotient. So let's take a look at dividing 344 by 5. It would go in 68 times with a remainder of 4. So that means mod 5, it's 4. It's just asking for the remainder. And div 5, it's asking for the quotient. So this would be 68. So these two functions are just asking for the remainder and the quotient. But let's look at a case where we have a negative integer that we're dividing by. You'd probably, when you divide a negative number by an integer, you'd probably just think of it as the positive. You would probably just take the 215, divide it by 7, it goes in 30 times, with a remainder of 1. With a remainder of 5, right? But negative 215 would then be negative on both sides. But that remainder isn't between 0 and our b, which is 7 in this case. So we have to change this a little bit. We would say 215. If we want to change this by adding 7, we'd get a plus 2 as our remainder. But if we add 7, we have to subtract 7. That bumps this down to negative 31 times 7. So for these ones, the answer to the mod would be 2, and the answer for the div would be negative 31. Okay. We'll see a little bit more of that later on, mostly the mod. We're not going to see the div really again. But we want to prove some statements about divisibility. And we'll remind ourselves, in general, if you say n divides m, this is the same as saying that m is equal to some multiple of k, some multiple of n, for some integer k. So in the first one, we have integers a, b, and c. If a divides b and a divides c, then a divides b plus c. So in each of these, we want to either prove or disprove them. In this one, it turns out you can prove it. So let's having an and statement is nice for the if part because we can assume both are true and use them to prove the conclusion. So if A divides B, then that means B is some multiple of A, so K times A, for some K in the integers. And A divides C, so that means C is also some multiple of A, so we'll say J times A for some J in the integers. And now we want to see that A divides B plus C. So if we take a look at B plus C, well, we can substitute in what we know. This is Ka plus Ja. And we can factor out the A. So this is K plus J times A. And since K plus J is an integer, since K and J are both integers, then we have that A divides the B plus C. So this statement is true. But what about pretty much the same statement, but changing the and to an or? Having an or at the beginning kind of makes this statement, or this part of the statement, weaker. If this was true, it would make the whole thing stronger. But we have less to work with because we only know one of them is true. And this ends up being false. You could pick some values. If I let A be 3, B equal to 6, and C equal to 7. Of course, there's many counterexamples here. We do have the first part because A divides B is true. But A doesn't divide C, but that's not a real problem because we have an or. We have a true or a false, which makes that whole thing false. But, so while this part is true, we don't have 3 dividing 6 plus 7, or A divides B plus C is false. So we have this part being true, the if part being true, and the then part being false, which makes the whole statement false. So part B wasn't true. Okay, a couple more of these. Next one, we have again that stronger statement that we have A divides B and C. We want to see that A divides B times C. This one ends up being true. Again, we have B is some multiple of A, and C is some multiple of A as well. Here, J and K are both integers. And then if we look at BC, well, that would be Ka times Ja. And we just need to see this as a multiple of A, so I'll just write this as Kja times A. We could say A squared, but we just want to see it as a multiple of A, so we don't have to go that far. Kja would be an integer. So that means A divides BC. But in the process of proving this, we see that it's, sort of overkill. We had 2 factors of A inside here. So that should mean that if I change the and to an or, that is probably also going to be true. But if you want to prove a statement where the if part has an or, it means you want to look at cases. So in case 1, we'll say the first one, A divides B. That means B is some multiple of A for some integer K. And then if I look at BC, this is Ka times C. So in particular, this is Kc times A, so it is a multiple of A. So therefore, A does divide BC. And case 2 is similar. We have A dividing C. That means C is a multiple of A. Notice I'm using the same K here because it's different cases, so I've sort of let go of this K and then brought it back. So So I'll put a line here to say these are separate arguments. And this time BC would be B times KA, since the C now is the multiple of A. But again, this time we have BK times A. We still get a multiple of A. So A divides BC. So in either case, we do have our conclusion. So the full statement is true. Next, we sort of have a, and this happens a lot when trying to prove things in mathematics. If you, while in the process of proving it, you actually see something stronger. We have the two copies of the A here. So sure, A divides BC, but really A squared divides BC. So we're just making a stronger statement now. We want to say that if A divides B and A divides C, A squared ends up dividing BC. So it's the same as this, just changing the A to A squared. And the proof is essentially the same. We have B is a multiple of A, C is a multiple of A for JK as integers, and then BC is KA times JA. But this time we want to completely pull out the A squared, so it's JK, or KJ, either way, times A squared. So that does mean A squared does divide BC. But this last one ends up being false. If A divides BC, does A divide B or A divide C? So the way to get this one, one counterexample, if you take A to be 4 and B to be 6, C to be 14. The idea here is I took a value that's got two factors of 2 in it, and then each one of these only has one factor of 2. So you do have 4 dividing 6 times 14, so the if part is true. But 4 doesn't divide 6, and 4 doesn't divide 14. So that's the opposite of this. By De Morgan's law, it would negate both of them and change the or to an and. So this statement isn't true, since we found a counterexample. And you could find many counterexamples. Just essentially pick a square here, like you could do 9, and then you could do 6 again and do something like something with only one factor of 3, so like 21. Okay. I think we'll continue on, just get both sections done in one video. Here we get to do some more modular arithmetic. This time, we're not going to do 46 to the 30 and then divide it by 9. That would take forever. We're going to use some properties of modular arithmetic. So if A is congruent to B mod n, so this statement is saying that when I divide A by n, I get a remainder of B. Actually, it's a little bit different. This says that n divides the difference between B and A. So that's more precisely what that mod statement is. So it doesn't necessarily have to be the remainder, but the difference between them has to be a multiple of n. So if this is true, then I can take both sides to any power. So A to the r would also be congruent to B to the r mod n. And you could do that by induction. If these two are already congruent, then multiply both sides by A, and then since A is congruent to B, multiply this side by B, so you get A squared is congruent to B squared, and then by induction it keeps going. You can always multiply by A and B on both sides. So this is nice because since 46, if I divide that by 9, that gives me a remainder of 1. So that means if I take it to any power, it would be the same as this to that power. So 46 to the 30th power would be congruent to 1 to the 30th power, mod 9. But, of course, 1 to any power is just 1. So this is just 1 mod 9. So it gives us a remainder of 1. So try that again with this one. The book does this one, or the Xi book does this one a little bit differently because it likes to work with only positive numbers for some reason. But you don't have to restrict yourself to that. You can look at negative numbers as well. So 38, what is that congruent to mod 3? Well, its remainder is 2, right? Goes in 12 times, giving a remainder of 2. But you could go further and say it also has, or it'd also be congruent to minus 1. Notice that if I take the difference between these two, I get 39, which is divisible by 3. And that's a better number to work with, because if I, just like taking 1 to a power, taking negative 1 to a power is just as easy. So 38 to the 7th power would be the same as minus 1 to the 7th power. But minus 1 to the 7th, since that's odd, it would still be minus 1. And then you can pull that back to being 2. So you do get a remainder of 2. So this actually brings up an important point about this congruence versus the mod as a function. Being congruent just means that the difference is a multiple of that, what we call the modulus. So minus 1 is an answer here. But if I want to think of it as a function only giving out one value, I want it to spit out the remainder that would be between 0 and 3, not including the 3. So we don't want the minus 1 as our final answer here. The modulus operation, it's not hard to see that it distributes through addition and multiplication. So I could do each of these mod 7. So 72 mod 7 times 65 mod 7 plus 211 mod 7. So here I'm thinking of mod as the function. There's no congruences going on here. But this whole thing would be congruent to doing each of these mods. So this gives me a remainder of 2. This one gives me a remainder of 2 as well. And this has a remainder of 1. So it would be congruent to this mod 7. And then this comes out to be 5. So our answer here is 5. Okay. Well, so far the examples we've seen have been fairly straightforward in the sense that we had 1 and minus 1 when we did the powers. Let's see what happens if you don't end up with 1 or minus 1. So first we look at 44 mod 6, and that has a remainder of 2 if I divide it by 6. So that means if I take it to the 12th, so 44 to the 12th is congruent to 2 to the 12th mod 6. But that means I still have to do some work. 2 to the 12th isn't exactly an easy number to work with. But you don't have to first find 2 to the 12th. We could split it up first. We could see that this is 2 to the 6th times 2 to the 6th. Oops, 2. And then go ahead and do each of these. Since 2 to the 6th isn't too bad, that's 64. And then, just like we saw here, it goes through multiplication. So each of these mod 6 would be a remainder of 4. So this is 4 times 4. Should put congruent signs each time. And 4 times 4 is 16. And I do one more mod 6, divide it by 6. And I get 2. Or sorry, I get 4. So it should have a remainder of 4 at the end. Ran out of room here, but this last one isn't too bad, so I'll just take that room. The reason why I did that is because that's not the only way you could have broken it down. I could have said that this is 2 to the 3rd to the 4th mod 6, since you would multiply exponents. And 2 to the third is 8. And once again, I can, reduce this mod 6, reduce the base mod 6. That's what we've been doing this whole time, just reducing the base by the modulus. So this is 2 to the fourth. So we get 16, which is the same as this step, so we get 4. So we actually get there in one less step doing it that way. Okay, and this last one ends up being not too bad. Again, because different from what the Zybooks does as the solution here. 17 is -1 mod 3, so similar to what we just saw with part B. So 17 to the 12th is -1 to the 12th mod 3. But that's an even power, so that's going to be 1. So taking numbers to powers and then reducing by a modulus is the basis of what's done in modern cryptography, or in how we encrypt information, because generally that's a difficult thing to do, taking something to a high power, and then taking its mod brings it back down to size, so you don't have some giant encryption. You still have a small encryption, but you do need to be able to go back. So once you encrypt something, you need to be able to return to where you started. So what these are is integers mod 7 and integers mod 8. In Zybooks, they have an example of doing 5 and 6, but I thought we'd go to the next level. So the idea is just coming up with tables. So if this is the addition table mod 7, then there's only 7 numbers here, or 7 possible remainders. Oops, 5 and 6. And then same here. And then you just add. So 0, 1. Adding 0 doesn't do anything really. 3, 4, 5, 6. And then adding 1. 1 plus 0, 1, 2. But when I get to 7, I'm still dividing by 7. So that comes down to 0. Do one more row here is 0 plus 2, 0 plus 2, 1 plus 2, 2 plus 2. But then 2 plus 5 would be 7. That's a remainder of 0. 2 plus 6 is 8, remainder, or divide by 7, remainder of 1. So instead of doing the whole thing here, I have all of these done already. So here's what you get for both. I'm just going to point out a few, particulars. So you get nice patterns for both the addition tables. So this is, both of these are for 7, both of these are mod 8. So you get this, what we call cyclical pattern. So each row is just a cyclical shift of the one before it. And same thing here. So these ones aren't all that interesting to look at. It's the multiplication tables that are much more interesting to look at. So for Z mod 7 here, I didn't include 0. You don't normally when you do a multiplication table. And you just have a row and a column of zeros. But compare the two that you get here for, well, let's take an example. Like if I did 4 times 5, that would be 20. But if I divide that by 7, I get a remainder of 6. So each one of these is the remainder after you do the multiplication. And over here, if I did 6 times 5, that would be 30, but mod 8, that would give a remainder of 6. So some takeaways here. Notice that in this table, there are no zeros. And in this table, there are. You have 2 times 4, which divided by 8 gives you 0. So you have a couple places here where there's zeros where you don't have any here. And also, in this table, every row is just a permutation, a rearrangement of our initial row. So every number appears in each of these rows. Well, that happens in some of them, like all the odd ones here actually are permutations. The even ones are not, especially 4 only has 0 and 4. And so that makes this one a better place to work in because, again, if we think of encryption, if you want to take, like, if your only things to encrypt are the numbers 0 through 6, and then multiplying by this gives you your encryption, or multiplying by one of them gives you your encryption, then you can always go backwards. But if you end up getting 0, how do you go backwards from that? At least in the multiplicative sense, you can't go backwards from 0. There's nothing you can multiply by the 0 to bring you back to where you started. So, of course, the numbers that you work with in encryption are massive. I'm only looking at 7 and 8 here. But the same principle applies. If you have a table like this, then the encryption works because you can decrypt it. But if you have a table like this, you're not going to always be able to. I believe we're going to come back to this, but let's move on for now. Oh, I basically answered this already, but we'll get to that in a second. So just some more, I wanted to add one more property that you can use in these types of problems. So let's do this as we normally would. 46, when I divide it by 7, it gives me a remainder of 4. So if I take it to the 10th power, it would be the same as taking 4 to the 10th power, mod 7. And let's do some stuff. I could also have called this minus 3 to the 10, but it's not really any better. So we'll stick with 4 to the 10. I'm going to change this to 4 squared to the 5th, mod 7, so that I can call that 16 to the 5th. And then reduce 16 mod 7, that gives me 2. So 2 to the 5th. And 2 to the 5th I can do, that's 32. And then finally that gives me a remainder of 4. Now what I want to do different here to get the answer again in slightly shorter amount of steps, I want to look at what's called Fermat's, and this is a bit extra, it's not actually in these sections, Fermat's little theorem. Or I usually abbreviate it as FLT. This is a very powerful theorem, especially when you're working mod a prime. So a raised to a prime is actually congruent to that base a if you're working mod that prime. Notice the main difference between 7 and 8 with this example is that 7 and prime is prime and 8 isn't. So whenever you have a prime that's going to be good, you're going to have something like this, where if you have a composite number, you're going to have zeros. And a lot of it is due to this theorem. So I'm working mod 7. So when I was doing 4 to the 10th, I could think of that as 4 to the 7th times 4 to the 3rd, since you add exponents. I'm working mod 7. So 4 to the 7th mod 7 is just 4. So that's using this property with a equals 4. And 4 to the 3rd is 64. So I can reduce that mod 7 and get 1. And so we get 4 again. Again, a little bit shorter amount of steps. Okay, the last one of these here, 34 to the 5th. Mod 9. 9 isn't prime, so I can't use this. This only works for primes. Although there is a version of this called Euler's theorem that works for non-primes. So first we reduce 34 mod 9. And you get a remainder of, 7? But I'd rather not use 7, because I'd have to do 7 to the 5th. So let's instead use minus 2, since it's also congruent to minus 2 mod 9. Again, the way it's congruent is if the difference is a multiple of 9, and 34 minus negative 2 is 36. That's a multiple of 9. And now I raise both sides to the 5th. So 34 to the 5th right here is minus 2 to the 5th, mod 9. We already saw 2 to the 5th over here was 32, so this is negative 32. And when you work that out, you get a remainder of 4. So it's pretty clear how to multiply and add in these different worlds. So mod 7, mod 8, we know how to multiply and add any of the numbers there. But can we do their inverses? Can we subtract or can we divide? Well, we can do these things as long as, you can essentially go backwards, right? So in both of these addition tables, notice each row is just a permutation of the one above it. So there's no duplicates in the row. If there was a duplicate, then there would be no way to go backwards uniquely. And that's what we mean by being well defined. So with addition, you can go backwards uniquely. So subtraction would be well defined in both cases. So subtraction is well defined in Z mod 7 and Z mod 8. And in fact, in any modulus, subtraction would be well defined. But division, if I want to take these numbers and divide, I could say, since 4 times 5 is 6, I could say 6 divided by 5 would be 4. 6 divided by 4 would be 5. So I can define division there without any problem, because there's no, if there's multiples here, like we have here, like 4 times 5 is 4, but 4 times 3 is also 4. So if I want to divide 4 by 4, it could be either of those. It could be any of 1, 3, 5, or 7. So that's not well defined. So division is well defined in Z8 or Z7, and really in any prime modulus, but not in Z8. And in particular, it wouldn't be defined in any composite modulus. Okay, that's it for this chapter. So next video we'll be starting into chapter 8.